Okay, answer to the question I posed, what's the direction of the velocity at this point? Yeah, that didn't get a real quick answer, so let's review what velocity is, because you probably haven't thought about velocity in 2 dimensions. Okay? And we probably need to address it. Okay, so if we have an r of t here and an r of t plus delta t, and this is our path, then the change in r is this, right? Well, that's our change in position, right? So what's the direction of our velocity? Our average velocity? Well, it's going to be the change in position divided by delta t, right? Okay, well, delta t is positive, so it's got to be a positive multiple of this vector, right? It's got to be in the direction of this vector. Now, we don't have a scale for time. This is in a position scale. I mean, for velocity, well, this is a position scale. Velocity is a different animal, right? So we can draw the average velocity vector any way we want to, okay? Of any length that we want to. So I'm going to draw the velocity vector. Oh, I'll make it a little longer. I could have made it shorter, but for the picture, I think a little longer might be clearer. Okay? So there's our average velocity, right? Now what's the instantaneous velocity? It's the derivative of the r function at this point, right? So what's your picture do if you want the derivative? Well, you shrink delta t. You take the limit as delta t goes to 0, right? What's that do? Well, shrink delta t, shrink it down to half, you have this point, right? So now your average velocity would be in this direction, probably about the same magnitude, okay? If it's a short delta t. Well, keep shrinking it, what happens? So we shrink it again, we shrink it again. You're going to approach the tangent vector, okay?
So is the velocity always tangent to the curve?
We just proved it, right? So, good statement, okay? So your velocity is tangent to your path, okay? I put an arrow on that, I shouldn't have, I just wanted to draw the tangent, right? But now I can draw the instantaneous velocity vector. Okay? Make sense? So we got to have that picture, and we got to understand that limit. Okay? As an engineer, you still want to understand that limit, so you understand what you're talking about when you talk about the limit, and when you think through a problem that has a limiting aspect to it. And it's best if you can do it rigorously, but, you know, the more rigorous, the better. Also, you got to learn your engineering. There's finite time in a day. Okay? So balance it out, but learn to do, I mean, I'm going to require you to do a certain amount of it. Okay?